So today we want to talk, in this section, we want to talk about this introduction to ensemble learning. And it's just an introduction, and you can go more deeply also into it. So the problem here, we have two problems in any machine learning model or any statistical models. For example, it's bias and variance. So we need to find a way to solve this bias and variance. In fact, bias, it can cause this underfitting if your model is biased. So it can lead to this kind of underfitting, for example, and the variance will lead to overfitting. And we know that underfitting, it's not a big problem because we just need to increase model complexity, for example, to get better results, or maybe we need to train our models more to try to enhance our results. And when it's variance, it's a problem because we have this overfitting problem, and overfitting problem, it's really a problem, which we need to, maybe the model is complex, too much complex. And in this case, we should follow the advice that we should start with a base model, for example, and this base model should be something just a little bit better than the ground truth, for example. And after that, we can increase the complexity step by step to enhance performance. So the bias, it refers to the inability of a method to correctly estimate the target. I have a model, and this model cannot predict the target, for example. It cannot classify it, or it cannot be predict or regress it, for example. So it's inability, which means this model is less competent or less complex, for example, and it does not have the capacity to correctly classify this problem or to predict my target values. And in machine learning, bias refers to the difference between the predictions and its target. So, and it's the error, it's a prediction error, correct? And the biased models cannot accurately fit the training data. It cannot accurately do this because it's underfitted, for example, resulting in poor ensemble training. And we have this ensemble and out sample. In sample, it's the training set, and out of sample, it's the testing set. So when we have this biased models, it will lead to a problem because it cannot accurately fit the training data, and it will result in poor ensemble and performance and out of sample performance. So both the accuracy for the testing and the training, it will be very low. And it's an indication of underfitting, correct? So when we calculate the prediction error, for example, or accuracy for training and testing, and both of them are low, in this case, we can see that the model has a problem of underfitting, or underfit my data. And the underfitting, in fact, it's due to the model simplicity. Maybe the model is too simple, right? It's a model simplicity and or lack of complexity. We need to have a model which is a little bit more complex to be able to map those underlying features of, or those complex mapping in my data set. So the model is too simple. So maybe I have a very complex models, which has some complex mapping between inputs and outputs, and my model is too simple, which cannot capture those mapping between inputs and outputs. And a good example of a biased model, it arises when we try to fit, for example, this is a sine function with a simple linear model. I have, as you can see here, it's a sine function. So the data, in fact, it follows a sine function. And I try to use very simple model, which is linear regression or something. So when the model is simple, it will just try to generate this. Okay, it will just try to. Maybe I need to select a different color. So so maybe this. I try to select a simple model. So this simple model will just create this line. So I will have too high difference between those predictions, because I will predict this one here. In fact, I will have those predictions here. So I will have this different, large difference between the predicted value and the actual value, as you can see it here. So I will have large difference between actual values and the predicted values, right? Those are the actual values, and the predicted values will be located in this line. So there will be too much or too large difference between the actual values and the predicted values, which is an indication that my model is underfit my data. So it's underfit my data because the model is very simple. This is linear model. It's omega x plus b. In fact, this line can be represented by omega x plus b, which is too simple, and it cannot capture those complex patterns in my data. I cannot create that. It cannot capture those mapping between inputs and outputs. because this is x, for example, and this is y, and the function it's y equals sine x. I need to get something like this one. But because my model is very, very simple, I will just try to find something which is omega x plus b. So at the end, it will be a linear model, which will be a straight line, and it will not be able to accurately predict my values. So the model cannot fit the sine function as it lacks the required complexity to do so. Thus, it will not be able to perform well in sample or out of sample. The performance will be very low for both the training data and the test set. So when you calculate the accuracy for test and the training, it will be very, very low, which is an indication of underfitting. On the other hand, variance is a concept from statistics which refers to how much individuals vary within a group. As an example, taking a sample from a population, the variance will indicate how much each individual value is different from the mean value when we have this variance. So can have the variance or standard deviation, for example. So when this value is large, it will indicate how much each individual value far from the mean value of the whole population. Because if I have a sample and I calculate the mean value, for example, and we can calculate the standard deviation or variance, for example, and this number, it will indicate how much each value is different from the mean value. In machine learning, variance refers to the model variability or sensitivity to data change. When you change the data, I mean the model will not be able to capture those changes, which means the model also suffers from those variance in predictions. This means that high variance models can generally fit the training data well and so achieve high ensemble performance. So the performance will be very, very good for the training data, but it will perform poorly out of sample, which is the performance for the test set or for the unseen data will be very, very low, which means, which is an indication of overfitting due to unnecessary models complexity. It's overfitting. So the performance for the training data will be very well, but for the test set, it will be very, very bad, which is an indication of overfitting. So how can we discover this? You just look into the accuracy for test and accuracy for training. If the accuracy for the training, it's very high, it could be, for example, 95%. And for the test set, it could be, for example, 60%. It's clearly an indication of overfitting problem because the model performed very well with the training, but it performed poorly for the test, right? We have an example here, a decision tree, for example. It can have high variance if it creates a rule for every single instance, correct, in the training data set. So, for example, because in this decision tree, we try to create a rule for the whole data set, for example. So, in fact, the decision tree, it will select some features and it will work with those. It will work with those features to make decisions. So, if it will create a rule for each data point, in this case, the performance will be very, very well for the training data, and it will perform very badly, really, for the test set, which is an indication of overfitting. Which means the model will be very sensitive to the data changes, correct? So it's model variability or sensitivity to data change. When you change the data, when you get unseen data, or when you try to test your model for the test set, and when the test set is a little bit different from the training data set, the performance will be very bad, or the model will be sensitive to small changes or even the errors or the noise in the data, because usually you are collecting some data and the data maybe it has some noise, for example. So the model will be very, very sensitive and it will not be able to predict those target values correctly. We should have this bias variance trade-off, because as we agreed that bias, it refers to underfitting, and variance, it refers to overfitting. And we need to get a model, we need to have a trade-off between this bias and variance, or between underfitting and overfitting, in order to get a model which can generalize well. So this trade-off, it refers to the fact that as the model complexity increases, its bias decreases, while its variance increases, right? Because when you increase the model complexity, the variance will decrease. When you increase the model complexity, it could lead to overfitting, right? which means the variance will increase, correct? The variance will increase. The model will be more sensitive to noise in my data set, but at the same time, also the bias will decrease because the model will be able to predict those target values correctly. So when you increase the model complexity, we should expect that maybe the model will overfit, which means that the variance will increase. The model will be more sensitive for data changes, but at the same time, also the bias will decrease because it will be able to correctly classify or predict those target values. To avoid this problem, we can use ensemble learning, and the ensemble learning is an approach which aims to address this high bias or variance by combining the predictions of many diverse models. If your model has a problem, we can use ensemble learning, and the ensemble learning we can train a set of models, and we can try to combine maybe the predictions from each models and try to find the best way for making our predictions. So in this approach, in fact, it's instead of relying on a single model, we can have ensemble models, ensemble learning, for example, where we have a number of models, and we can just use a voting approach, for example, to get those predictions. So instead of using a single model, we can use a number of models and use voting, for example, to find the right decision. So the bias and variance are two of the three major components that comprise this model's error. The third one is called a reducible error, which is attributed to inherent randomness, noise, and variability in the data. So the mean square error, for example, or error, it consists of variance and bias square, for example. Bias and variance stem from the same source. It's model complexity, while a bias arises from too little complexity. I mean, the variance, it's coming from the model complexity, while the bias, it arises from the little complexity and the freedom. So when your model is too little complex, it will lead to high bias, and when the model is too complex, it will lead to high variance. So we need to have a trade-off between bias and variance, or between complexity and the little complexity, in order to get a model which has satisfactory performance. So variance arises from two complex models, and therefore it's not possible to reduce bias without increasing variance and vice versa. So there is an optimal point of complexity where the error is, I mean, we have this in this graph, for example, this is a model complexity, and we have in the y-axis, we have the error. So when it's too little complex, what will happen? When the model is located here, we should expect that the bias will be higher, correct? So the bias here in this line, I mean, the bias will be higher here when the model is too complex, because here we can have this underfitting problem. So the model will not be able to correctly predict those target values. And when you increase complexity, the bias will decrease, right? So when the model is less complex, we will have high bias. And when you increase the model complexity, we will get less bias, because the model here will be able to correctly classify those points, for example, or predict those values. But at the same time, also the variance, when the model is less complex, the variance will be very little, because the model will be able to generalize very well. Because this variance, it's about generalization. So when the model complexity is less, the model will be able to generalize very well. But when the model complexity increases, the variance will increase. And at some point, the model here will overfit, right? So in fact, we need to find a trade point between those two. So we can calculate the error, which will be the variance plus bias square. So this green line, in fact, it's the summation of the other two curves. So this green line, it's a variance plus bias square, for example. So we need to find a point where we can get a minimum error. So the minimum error here is when you look into this green curve, we can say that the minimum value will be here. So we need to get this performance. So this performance will be a very satisfactory performance, because in this case, the model will perform best both for in-sample and out-of-sample performance. So the model here will have good performance. It will not underfit, and at the same time, it will not overfit. So we need to get that point. So we need to reach this optimal point we need to stick to this point, because here the model performance will be satisfactory, it will not underfit, and it will not overfit. As a result, as it is seen here, the error can never be reduced to zero. It will be very difficult to get zero error, right? Because we need to reach this place. One way for solving this problem is to use ensemble learning, and ensemble learning it involves a collection of machine learning methods which aim at improving the prediction performance of the algorithm by combining many models. We need to combine many models so we can have different point of views, and we can just take voting, for example. If we need to classify something, we can ask each model, how can you classify this one? And at the end, we will vote. For example, in this case, we will try to reduce this bias and variance. So by combining different diverse models in an ensemble, we can reduce the expected error of the group, which we call the ensemble's error, while each individual model remains unchanged. So it has its own bias and variance. We will not change those models, but we will have a collection of models, and we will try to use the outputs from each models and combine the outputs or the predictions from each model to create one decision or one prediction. So we should expect that this is in this x-axis, we have this number of base learners, because the ensemble, it consists of a number of base learners. If you have a single model, we should expect very high error for a single model. This is our traditional way for work. When we have a single model, we should expect a very high error. But when you try to increase the number of learners, we should expect that the error will decrease. So when it's 3 learners, for example, base learners, we should expect that the error will decrease to this value when it's 5, 7, 8, 9, and so on. So when you increase the size of your the size or the number of your base learners, we should expect that the prediction error or the ensemble error will decrease, and you will get maybe the correct decision as much as possible. So the ensemble methods, I will just describe one approach today, but they are divided into 2 major classes or taxonomies. For example, it's called the non-generative methods and generative methods. And the non-generative, it's methods which focus on combining the predictions of a set of pre-trained models. We will have a set of models, and we will try to combine the predictions of from those models that are usually trained independently of one another. I mean, we have a set of models. For example, model number 1, model number 2, model number 3. Those models will be trained independently from each other, and we will create ensemble, and this ensemble will consist of a number of base learners or models. So we will use those, for example, 3 models or 4 models we will combine the predictions from those models to make a final decision. So the ensemble algorithm will dictate how their predictions will be combined. In this ensemble approach, we will just try to find a way to combine the predictions from each individual model to make a single decision at the end. The second method, it's generative, and it's able to generate and affect the base learners. In this approach, they try to optimize the performance of each learner by maybe tuning their learning algorithm, or maybe try also to change the data set which used for training them in order to ensure diversity and high model performance. We will focus on this non-generative approach because this is very, very simple, but also for you, maybe you can go into those approach if you want to maybe write a paper in ensemble learning, for example. This is very, very simple approach, and it's nice, and it gives you more confidence in your results when you are using this ensemble approach. It's like making a decision. For example, I want to make a decision for investing in the future, so maybe I can make the decision by myself. In this case, maybe the error will be very, very high, risks will be very high, right? We can say it like this. You want to make a decision, for example, you want to invest in the stock market, for example, and you need to make selections of your, which one should I put my money in that one, for example. If you will do your decision by yourself, maybe risks will be very high. So it's better really to discuss with other experts. You have some experience, you need to get maybe some colleagues or some friends. You need to discuss with them. So the collection, when you are a group of people, maybe the decision will be more correctly. In this case, risks will be much less. So we will have some examples of non-generative methods. We have this voting and the staking, for example, and in voting, where the model vote in order to produce a single answer. I have a number of models. So maybe model 1, I need to classify, I have an image and I want to classify it into dogs and cats, for example. So I have model 1, model 2, model 3. Maybe model 1, he will vote for, he will say it's cat, this image is cat. Model 2 will say no, it's dog. Maybe model 3, he will say no, this is cat. So in this case, according to this voting approach, I can just say that, okay, based on this, I have 2 votes for cat and 1 vote for dog. So this image will be classified as cat, right? So it's called the hard voting approach, for example. So this is one approach. Stacking, where is a model, which is a meta learner, to learn how to best combine the base learner's predictions is generated or developed. The new model does not affect the base learners, and therefore it's non-generative approach. This is stacking. In fact, I will train a meta learner or a model, another model, and this model will learn how to combine the decisions or the predictions from those 3 models into one single decision. So it will not affect the 3 models, but it will try to find the best way for stacking or combining the decisions from each individual model. I will talk about those generative approaches. For example, it's bagging and boosting and random forest. So you just, if you want to go, I will not go into those approaches, but if you want to go, you can just find how to do this. It's a very simple approaches also. So bagging, for example, it aims to reduce variance by resampling instances of the training data set, creating many individual and diverse data sets originating from the same data sets. So it works on the data set, try to resample and try to create different data sets which can be used for training different models. Afterwards, a separate model is trained on each sampled data set, forcing diversity between the ensemble models. Boosting is a technique which is targeting biased models. Its main idea is to sequentially generate models such that each new model addresses bias inherent in the previous models. So by iteratively correcting the previous errors, the final ensemble has a significant lower bias. So this boosting, it's a focus. It will focus on solving this bias problem. Random forest, for example, it's similar to bagging in the sense that it resamples from the training data sets. However, instead of resampling instances, it will sample features, right? Thus creating even more diverse trees, as features strongly correlated to the target, maybe some correlated features which are strongly correlated to the target may be absent in many trees. So in this random forest, you can just get different trees, and from those different trees, you can combine the decisions to create a single decision. Difficulty, which in ensemble learning can greatly increase the performance of machine learning models, but it comes also with some cost. Some difficulties are as follows. So it's weak, and we have a problem when our data it's weak or noisy data. If the data contains noise or incomplete information, there is no single machine learning technique which will generate a high performance model. So if we have this problem, if your data set is weak or it's noisy, just give up. I mean, because they call it how do you call it? Shit in, shit out, something like this. I don't remember. So when your data set has a problem, it's noisy and it's weak, there is no way to get a good model. In fact, in this case, you need to go back and collect data, right? So this is a problem about data. When your data is not good, in fact, we should not expect you that you will create a fancy model or a good model, because anyway, your data, which is a source of information, it's noisy and it's weak, right? Correct? Maybe this week is wrong, right? So if the data contains noisy or incomplete information, there is no way to create a single model which will perform well, right? Because anyway, I mean, it's rubbish, and yeah, they call it rubbish in, rubbish out, right? So they call it rubbish in, rubbish out. So if your data is bad, we should not expect you that you will get a good model, right? So they call it rubbish in, rubbish out. Number 2, understanding interpretability. By employing this large number of models, interpretability will be reduced, because when you have a single model, it will be easy to understand how decisions are made. But when you have a set of models, it will be really very difficult. So it will impact interpretability. So interpretability will be reduced. So for example, a single decision tree can easily explain how it produced a prediction, but following the decisions made at each node, for example, by following the decision made at each node, on the other hand, it's difficult to interpret when you have an ensemble which consists of 1,000 trees to try to predict a single value. So complexity, when you have ensemble, complexity will increases, and then when complexity increases, interpretability will be reduced. It will be very difficult to understand. Why it classifies this one as a cat or dog, for example, because it's too complex. Number 3 is the computational cost. When you are training a single model, it will be, of course, it will be affordable. But when you try to train 1,000 models, for example, it will require maybe 1,000 times more computational resources. So computational cost will be high, in fact. It's not only computational cost, but also time, in fact, right? Because if I need to train a single model, maybe it will take maybe some time, for example, but if I need to train 1,000 models, it will take much more time and it will require higher computational cost. But of course, the advantage here is that you will get more reliable decisions, because I will make decisions based on, by combining the decisions from each individual model. You need also to choose the right models. Choosing the right model, in the ensemble must possesses also certain characteristics. There is no point in creating any ensemble from a number of identical models. You cannot select the same models. So, for example, I cannot say that I will have an ensemble of 10 perceptrons, because we should not expect any difference, right? Because it's like training a model using different random initial values, for example. So we should not expect too much difference between those models. So we need to choose and generate the right models due to the large initial hyperparameters that are usually selected by the analyst. You cannot select identical models in your ensemble. So you need to select different stuff. So, for example, I can select a perceptron, a multi-layer perceptron, a support vector machine, for example. So in this case, you need to select different models to expect different results. But if we will select 5 models, 5 identical models, which we will not expect any difference between those models, and we will get almost the same results as a single model. So we will talk about some of those non-generative approaches, which is a majority voting. This majority voting is non-generative approach. And this majority voting is the simplest ensemble learning technique, which allow you to combine the outputs of multiple Bayes learners. And in majority voting, the aim here is to output the most popular or most voted for, of the Bayes learners prediction. If I have 3 models, and the 2 models selected this image as class A, for example, we will just classify it as A, correct? And in this case, in fact, we need to have maybe odd number of models, because we have this majority voting. So it's better to have this odd number of models or Bayes learners. And it's similar to how elections work. The algorithm assumes that each Bayes learner is a vector and each class is a contender. So the algorithm takes votes into considerations in order to elect a contender as a winner. There are 2 main approaches to combine those multiple predictions. We have this hard voting and soft voting. So this voting approach, or majority voting, there are 2 approaches. It's hard voting and soft voting. Hard voting, we just count votes. But in case of soft voting, we'll try to consider probability. This is the hard voting. Hard voting combines number of predictions by assuming that the most voted class is the winner. And in a sample case of 2 classes and 3 Bayes learners, I have here 3 Bayes learners, model 1, model 2, model 3. And each model will vote. I have an input image, for example, and it's binary classification problem. So this image should be classified either A or B, for example. And in this case, I have 2 models which vote for this image to be class A, right? So I have two votes as A and 1 vote as B. So according to this hard voting approach, we will just count those votes for each target class, and it will be classified according to the highest one. So I have 1 as B and 2 as A. So in this case, this image or this example will be classified as A. Very simple approach. And it's like elections. So as you can see, this hard voting approach is very, very simple, and it can be used on those, maybe classification problems, for example. So as I told you, we need to have an odd number of learners, because if you selected 4, for example, if you have 4, what would be the situation of 2 voted for A and 2 voted for B? So which one should we select? So it's very, very important to have here odd number of models or learners. So number of learners should be odd number. Number of learners should be odd number. Should be 3, 5, 7, and so on. We have this example. We say that there are 3 different base learners who are predicting whether a sample belongs to one of the 3 classes. I have 3 learners, and we have 3 classes. And I have maybe an image or an instance, for example. So learner 1, he will calculate the probability, because we will use this soft, we will use the soft layer, for example. So we need to calculate the probability. As you can see, for learner 1, the summation of the probability each time equal 1. 0.5 plus 0.3, 0.2 equal 1. This one, it's 0 plus 0.48 plus 0.52 equal 1. 0.4 plus 0.3, 0.3 equal 1. So the summation of the probabilities equal 1, correct? So maybe the model is anyhow, in the output layer, we will have this soft max, correct? So we have here class A, class B. This is A, B, C, and we use those soft max layer, for example. So the output here will be probabilities, and it will add to 1. So for model number 1, you will say it's A by 0.5. It should be A, B by 0.3%, 30% it's B, and it's 20% it's a C. So in this case, we can say that learner 1, we will take maximum of this line because it's 0.5, 0.3. We can use this argmax, for example. We can say that now it's A. So learner 1 or model 1, he selected this image as class A, correct? Because this is the highest. We will go to class B or learner 2, for example. He will vote for, or the probability that this image is A, it's 0. It's B by 0.48. No, this one it's 52%. It's a C. So this one it's the maximum, right? So it will be like, okay, this is C. We will go for the learner number 3. Learner number 3, he will classify this image as 40% as A, 30% as B, 30% as C. So this one it's the maximum. So we can say that this one also, he will vote for this one as A. So in this case, we will count votes. So at the end, we will see that we have 2 votes because we will take this argmax. In this case, when using this argmax, it will select this one. So it will select class A. It will select here class C. It will select class A. So we have 2 class A and 1 class B. So in this case, it will be classified as A. This image, according to hard voting, it will be classified as A. So now we have 3 models, and each model will have, its own choices, and we will count the votes at the end, right? Yes. So this one will be classified as A. So just remember, we have 2 votes for A and 1 voted for C. So the final prediction will be A, will be class A. So this is the hard voting. So this one, we call it hard voting. This one, it's hard voting. In case of soft voting, it takes into account the probability of the predicted class. And in order to combine the predictions, soft voting calculates the average probability of each class and assumes that the winner is the class with the highest average probability, right? So we will go back to this example again. We will calculate here the average accuracy for class A. So this one, it's 0.5 plus 0 plus 0.4. So it's 0.9 divided by 3. So we'll calculate the probability for class A. We will calculate the probability for class B. We will calculate the probability for class C. And we will take the argmax. We will take the, when it's higher, we will take the max. And we will return the class which has the highest average probability. So in this example, it's the same example. We will take consideration of the predicted probability of each class and average them across each learner. So this is the average. So this is 0.50, 0.3. So it will be divided, it's 0.9 divided by 3. So it will be 0.3. For class B, this one 0.3, 0.48, 0.3. So it will be 0.36, right? For class C, it will be 0.2 plus 0.52 plus 0.3. So it will be 0.34. As you can see here, this one, it's the max, correct? So when this one, it's the max, which means this class will be classified as this image will be classified as B, right? Also, this one, I mean, learner 1, he classified it as A. Learner 2, he selected C, because, I mean, in fact, we have B here, although we don't have no model selected B, because learner 1, he selected A. Learner 2, he selected C. Learner 3 selected A. But according to the soft voting approach, we will select B. We will select it as B, although we don't have any model which has selected B at all, right? So, so this is how soft voting works. So class B is not selected by any base learners as the predicted class, but by combining the predicted probabilities, class B has been chosen as the best compromise between the predictions. This is the best compromise. So for soft voting, to be more efficient or effective than hard voting, the base classifiers must produce good estimates regarding the probabilities that a sample belongs to us. It's very, very important because, for example, if we have a problem in learner 2, because in fact we have the problem from here, because learner 2, he selected C, but he gave also high probability to class B, right? In this model, he gave very high probability for class B. He didn't select B at all. He selected C, but at the same time, he gave high probability to class B. So if you have a problem in one model, it will really damage your results. So you need to train your models carefully, and you need to try to get better or accurate probabilities, because using this average approach or this soft voting approach, it might lead to problems. Because here in this example, we selected a class which has not been selected by any learners. But when we try to average probabilities, this class will be selected as output. So how can you develop this voting ensembles in Python? We have just voting. I'm talking about voting a classifier, for example, but other approaches also need to, maybe you need to go more deeply into it if you want to use it. This voting classifier, we can select it from sklearn.ensemble. So from sklearn.ensemble, we can import voting classifier. If you want it for classification problems, you will select the voting classifier. If your problem is regression, you can just use voting regressor. So we have two choices for classification problems and for regression problem. For classification, you will select voting classifier, and for regression problems, you will select voting regressor. After that, you need to create this voting classifier with hard voting. So I will have this voting classifier, for example, and I need to select the learners, for example. So maybe I need to use KNN, key nearest neighborhood, as learner number 1. I need to use a perceptron. I need to use support vector machine. I need to use MLP, multi-layer perceptron. And the voting equal hard or soft. If you want to make hard voting, you need to write here voting equal hard. If you want to make soft voting, in this case, you need to select voting equal soft. It will be the same function, but you need to change voting from hard to soft. The estimators or the learners should be different. I cannot use KNN1 and the KNN2 because it might be the same. Of course, I can use MLB with different structure. So I can use, for example, MLB as learner 4, MLB as learner 5, but maybe this learner 4 and the 5 will be different. Maybe one has 2 hidden layers and the one has 4 hidden layers or 3 hidden layers. So it should be good, but we should try to avoid having those base learners from the same type, because it will not make any sense for the ensemble learning. After doing this, we need to divide my data into training and testing, and you will use this training set for training your hard voting classifier. So here I defined a voting classifier, this hard voting classifier and soft voting classifier. I will use my data for training it, right? And after that, I will use this one for calculating predictions. So I will use X-test for calculating the predictions from the hard voting and the soft voting. And after that, I will just report my results. I will calculate accuracy, for example, using X-test and those Y-test and Y predictions, hard predictions and soft predictions. We will calculate those accuracies. But remember also, we have a problem here because we will put our results as a single number, which might not be correct, right? Try to calculate confidence interval so you can have this range. Yes, I guess we finished with this one, but I want to maybe open this example and try to, yes. Please, if you have any questions, do you have any questions? So I need to close this. I need to get this. Can you see my screen, please?
Yes.
Yes. Can you see my this GitHub?
Yep.
Okay, this is very good. So this is the example which we need to just check. I have a problem here in my mouse. Strange. Okay, so I will just. So I need to open this in Google Colab, for example. So I need to implement hard and soft voting classifier. So I'm just importing in NumPy, for example, and this is the sklearn. I need to import data sets, right? And I need to import linear model, support vector machine, neighbors, because I need to use KNN, for example. I will import also MLB classifier from sklearn.neural network. I will import the train test split from model selection. I will import voting classifier from ensemble and voting regressor from ensemble, just in case if you have a regression problem, you need to use voting regressor, not voting classifier. And the metric which I need to calculate the accuracy score, confusion matrix. I need to plot the confusion matrix. I need also to can get this classification report, for example. And if you need to plot something, you can just do this. So I will run that part. Maybe I need to change the runtime into choose a different runtime. Yes, I have a GPU. So now we are running that part. Oh, we have a problem here. Why? Why this one is not working? Plot confusion matrix from a scalar metric. What is the problem? Cannot import? Why? Confusion matrix, it's not from why? Plot confusion matrix is not in sklearn.metric. Maybe I need to. So okay, we will just do it without plotting. Plot confusion matrix. Yeah, it's metric. So what is the problem? Plot confusion matrix. So what is the problem? Because we should import it from metrics. Plot confusion matrix. So why it's not working here? I cannot. One more time, please. So is there any problem for plot confusion matrix? We cannot import it from sklearn.metrics. Is there any changes? I don't know really, but I can just comment it.
There was a comment. There was a comment on the sklearn side that it would be deprecated.
Which one?
If you switch to your other window, there was a note about deprecation. Will be removed in 1.2.
From estimator. Oh, deprecated will be removed in use one of the following. Oh, it's from predictions or from estimator. What does this one mean?
I don't know.
Yeah. Confusion matrix, plot confusion matrix. So we have this plot confusion matrix. So he imported it here from the same, right? Plot confusion matrix. So what is the problem here? Right, we are doing the same, correct? Should I just write it in one line, for example?
I guess this example is old. So
this one is old?
I suppose so. But if you would downgrade sklearn.
Oh yeah. It's called now confusion matrix display, right?
Yeah.
From estimator. So it's confusion matrix. Okay. But maybe you need to make some changes. So maybe you need to have it like this, right? So should also write here from estimator. Anyway, we can just use this one. Okay, so we can just try this. Yes, okay, so this is, we need to load our data set. It's a breast cancer data set. Right. So this is the size of the data set. We have 30 features, correct? 569 examples. And it's maybe it's binary classification problem. So we need to define those learners. So I have learner 1, 2, 3, and 4. The first one, it's KNN. And I selected number of neighbors equal 5. It's perceptron, for example, support vector machine. I used this kernel equal RBF, radial basis function. I used also MLB classifier, and this is 2 hidden layers. The first is 50, the second is 10. And I used activation logistics, correct? So and the fit each classifier, you need to train each classifier. I mean, when you import the data here, it's already divided, right? X and Y. And maybe the first split the training test samples. So test sample will be 100, but you can, I mean, I just use the here train test split, right? We use the here train, so forget about that part, right? So I just use the here, 25% will be used for testing, 75% will be used for training. We use the stratify. So so we will train each model, and after that we will test the prediction, the performance of each model. So now the accuracy of the first model, it's 93%. And the accuracy score of the second model is 85%. We can just multiply this one by 100 to make it easy. The third model will be 90%. This fourth model will be 93%, right? Now we need to create this voting classifier with hard voting and for soft voting. We will start with hard voting. So those are the estimators, KNN, perceptron, SF, support vector machine, MLB. Voting is hard voting. And you can also select weights. So in fact, if you know that I have a good high quality model, you can increase the weights of one model and you can decrease the weights of the second model. So this weights, it will reflect the importance of each model. So some models should be counted more. For example, the votes from some models should be weighted higher compared to other models because maybe some models has been trained with low quality data, for example. You don't trust it, for example. So weights also is very important here. So after that, after building this ensemble classifier, we will train it using X-train, Y-train, and after that we will do predictions. So in this case, we will have this hard voting from each model. I mean, it will be combined automatically. So the confusion matrix here is not working. So we need to confusion matrix display. I don't know. Because in this case, we need to get X test, Y test, right? Okay, do we have X test, Y test? What is CLF? It's model? Yeah, this is a model. This is correct. So maybe I will try to just maybe just CLF is not the CLF. Okay. No, I need to get this classifier here. Still also not working.
Because the X is small later.
Hmm?
Because the X is small later.
Yeah, this is correct. So this one should be X small. Okay. Oh, sorry. This one should be X. X small and Y small. Yes. So this is the hard voting accuracy. It will be 90%, right? And this is a confusion matrix. So 48 will be correctly classified. It's 0, does not have the disease and classified as 0. 81 with the disease classified as positive. So 48 negative, 81 positive classified as positive, and the model is confused on those 9 and 5. Of course, it would be nice if we can plot maybe the confusion matrix for those, but 902. It looks like that we choose L3, correct? Can you see this hard voting? So maybe they are selected selecting, do you see this L3? So based on those hard voting, maybe we select, I don't know how they calculate this accuracy, but I guess this number, it's exactly the same as L3. So in this case, we are selecting those votes by L3. This one is higher accuracy, but has not been selected. This one is higher accuracy, has not been selected. So according to this approach, maybe we selected L3, which is for classifying. So L3 is learner number 3 is what? It's support vector machine, right? So maybe support vector machine is providing maybe much better results compared to other models. So maybe I don't know. Should we use this one or no? I don't know. Yeah. So okay. Now we have our results. So this is hard voting. This is hard voting. If you want to use soft voting, it will be also. It's just a different way for doing it. I mean, I can define my classifiers like this one. So KNN, support vector machine, MLP. I removed the perceptron from this soft voting because the perceptron will not calculate a probability, right? The perceptron will not calculate probability. In this soft voting, we need to get probabilities. So we need to include models which calculate probabilities. So we will build our ensemble classifier. We will call it voting soft classifier. So it is a voting classifier. We have the estimators, voting equals soft, and also those weights. So we can change. We have 3 models. So I just put some weights which is equal to 1. For example, the summation equal to 1. So they have also the same values, but I give more weight to MLP, for example. It's the same also, we calculate the confusion matrix. Plot the confusion matrix will not work like this one. We need to get this one here. So it will be like this one. And we will comment to this one. So we will do it. So as you can see here, this is the precision recall. You can have this nice function for printing those confusion matrix. So first we have the soft predictions. We will get those soft predictions using X-test, and we will calculate the accuracy score for Y-test and soft predictions. We have this confusion matrix. We have the precision recall and F1 score for, I don't know for which model. And finally, we have the same. In fact, it's exactly the same as the confusion matrix which we got here using the hard voting. And the accuracy here will be 0.3 something. Is it higher or lower than this one? Yeah, it's different, but it's 92%. 92%, and it's better than this one, which is 90%. 59, but we have exactly the same results. If you can look into the confusion matrix, we have 48 negative classified as negative, 81 positive classified as positive. We have exactly the same numbers. This one, if type 2 error, type 1 error, can you find the type 1 error and the type 2 error here from this confusion matrix? So we have 9 positive classified as negative. We have 5 negative classified as positive. So where is type 1 error and type 2 error? Yeah, can you see the? Can you see my screen, please?
So I think type 1 error is the negative predicted as positive.
Yes.
5.
And the type 2 error, it's a positive, 9 positive classified as negative, which is more dangerous, right? Because we have 9 ladies, for example, they are positive, but they are classified as negative. So they will not take medications, they will not stay in the hospital. So it will be really very dangerous for them. So this is type 2 error. Yes. Do you have any question for this part? I don't know. We got this table. I don't know how can we. Oh, is this classification report? Yes. So we have this command, a nice command called the classification report. So the input to this classification report will be Y-test and soft prediction. So this this line, it will generate you this nice, you have accuracy, you have, and if we change it, if we can change this one, I don't know if it will. So for example, we can, if I will select it 1, 1, for example, so it's just equal. If I can select it, all have the same weight, for example. We will see if we will get different results. So we got the same results, right? We got the same results. So in this case, if you will use this ensemble learning also, I mean, your results will be more trusted because I'm not taking a single vote, for example, I'm not relying on a single model, but I will have an ensemble of different types of models. And those models, we will try to combine the decisions. We will create a single decision by integrating the decisions from those different models, or by combining the decisions from those different models. So ensemble learning, it's a very nice way, and your results will be more trusted because we are not relying on a single voter, for example, but we have multiple, so results will be more reliable. Yes. So do you have any questions, please? We made some changes here, so I will just store it in GitHub again. So if you want to get access to the same file, it will be this voting classifier. So now we have the same. So it's updated now because we changed this rule confusion matrix. Now we have confusion matrix display. So please, do you have any questions? Any questions in ensemble learning?
No, I think this was good to see.
Yes, thank you very much. I guess it's nice to, if you are working in a paper or something, for example, try to use ensemble learning. If you did something using some approaches, maybe you can repeat it using ensemble learning. Maybe you add new section in your paper, in your results, you expand your paper, for example, or maybe you can just write a brand new paper using ensemble learning. So you have the same data set, you have been working with some models in your head, for example, you got some results, you can repeat this using ensemble learning and try to make comparisons. Maybe you can write a new paper, or you can just make some comparative study between different types of approaches. So in this case, you will get more results. So this is a nice approach. So today we talk about this confidence interval and how can we report our results as a range, for example, which will give people more trust and our results will be more reliable, and also using ensemble learning to try to minimize or reduce bias and variance in our performance, in our model performance. So if you don't have any questions, we can just take another 10 minutes break and we can start again after, we can start at 11:05, for example. Is it okay?
I would have.
Yes, please.
Could you quickly explain again why the accuracy of the hard voting, the final accuracy, is the same as the accuracy of the third model? I think I didn't understand that.
Yeah, because it's similar to the example which we used in the PowerPoint. Because I don't know really. Maybe they will calculate this accuracy. I'm not sure if it is the accuracy of L3 or not, right? Because in this case, we need to do it for each example. I need to do it for the test example, for example, and I need to know. I need to know the hard voting from. I mean, if we need to test it, we need to go for each example in my test set, and I need to find the votes for each example. Because my understanding to it, maybe it's not L3, it's not connected with learner number 3, but they will do this hard voting. So for each example in the test set, they will calculate the votes, for example, and at the end they will calculate the accuracy, right? Maybe by chance it's the same as L3, because it's strange, it's the same number in fact. maybe it's by chance, right? Maybe it's not correct. It's not L3 exactly, but by chance. Because here, how it works here, we will go for the test set, and we will calculate the predictions for each example by example, and at the end we will calculate examples which are correctly classified and calculate the accuracy, right? So maybe it's by chance. It's the same as L3, but it might not be the votes of L3 because it's hard voting, right? So
Okay.
we have 4 models. So maybe for the first example, we got L1, L2 because it's a binary classification problem. So just imagine that in the first example, L1 and L3, they voted for class 1. And we have a problem here also because it's 4 models, right?
Yes, exactly. That's also something that I was wondering.
Yes, also because we need to select odd number of models because it's strange. Should be 3 or 5, for example. So maybe we need to add 1 more model here, and we need to test it for each example. So we will go for first example, and we will see maybe L1 and L2 they voted for class A, L3 and L4 voted for class B, but we need to have odd number, right? Because we need to have this hard voting. Maybe for I will just assume that it's L1, L2, L3 they voted for class A, L4 voted for class B. So in this case, example 1 will be A. We will go to the second example. In the second example, maybe L2, L3, L4 voted for A, and L1 voted for B. So in this case, we will have A. Maybe the second example, it will be B. So we will do it for the whole data set. And at the end, we will calculate the accuracy between. But in fact, we can do this by, I will just print this hard predictions, right? We can just print this one. Maybe we don't need to print it. So do you see? Okay, I will call it hard prediction. Hard predictions, and we will do it also for actual predictions, right? When it's actual, because we can actual predictions, it will be what? Y-test, right? It will be Y-test. If we need to calculate accuracy, how can we calculate accuracy? It would be Y-test minus Y, maybe NB dot what? Count? Do you have this count or what? I don't know. It's Y-test minus. I need to do this. I need to find how many cases not equal, right? Hard predictions. How can we count those events? Dot sum? NP.
Or NP dot sum, yeah.
Dot sum divided by the size of divided by what? Divided by the size of my data set. So it's X, it's Y train dot Y dot length, for example, or dot shape. I don't know. Should we make it like this? We will see. Hard prediction. Why hard prediction? Because we okay. Sorry. Do you see here? This is the hard predictions, and this is the actual predictions. And we need to print this accuracy. This is the error. Print. It's 1 minus. This is not accuracy. This is error. Correct. This is prediction error. Correct. because this is the cases where y test not equal to y predict. So this is the number of cases where we have something minus error. We need to multiply it by 100%, correct? Multiply it by 100. So 96%. So why do we have this number here? So do you see the accuracy here? It's 96%. Are the predictions? So please, can you explain to me why we have this? Accuracy score. What is this? Y test? How the prediction? So can you explain this one, please? So hard predictions, we got this hard predictions from this voting classifier using X test. And I will just count number of cases where Y test not equal to Y predict. So this is number of misclassified cases. This one, it's number of misclassified cases. So, and this error here, as you can see, it's, I will multiply it by 100 to be in percentage. So it's a 3.2% misclassified. So the accuracy will be 96%. So how can we get this number here? I don't know. How can we get this number? And if I want to get only number of cases, I need to get this one.
Yeah, it seems like there's really an issue because the number is literally exactly the same as the third model.
Yes, and I need to get those. Just 1 second, please. I will just print this one. So we will get number of cases which is misclassified. It's 14, and the 14 it's 5 plus 9, correct? Those 14, it's a number of cases which is misclassified, which is 5 plus 9. Can you see it? 14. So in fact, the accuracy, it's 96%. The accuracy is 96%. It's not 90%. So I don't know why we got this number here. Y test and hard prediction. Why we have this number? Is there any problem in this function? Accuracy dot score? Because from this confusion matrix, the accuracy will be 48 plus 81 divided by the total sum, right? Number of examples. So in fact, the accuracy, it's not 90% at all. It's not 90%. Hard predictions.
Perhaps check the accuracy score function.
Is this function?
No, I don't know either. But
yeah, because what is the problem in this function? Yeah, accuracy score. So the input to it is Y true, Y predict. Normalize, sample weight. What is normalized? It's by default, it's true. 1D array-like label indicator. So it's Y test, Y true, Y predict. Returns the fraction of correctly classified samples.
no. It seems correct then.
Normalize equal true? What do you mean? Should we use this one, normalize equal true? I don't know. Because it does not, I mean, we have those Y predict, Y true, and it will just calculate the accuracy because 0 plus fill is 0. So it's a 50% accuracy, right? Because those two examples are correctly classified otherwise. So what is the problem, Amy? It's really good notes from you and Y test, and we have here Y test and Y. This is Y test, and we are printing here Y test and hard predictions. So why is this? Why you are not getting? I don't know. Normalize equal true. Why it's not working? It's not defined.
You have 2 equals.
Oh yes, this one. It's still the same. Also, I cannot understand why this function returns this number. And also here, also in fact, it's 92%. How can we get this number here? Accuracy score. Soft prediction. It's a voting soft X test. So because also we should get the same accuracy here. It's not 92% at all. It's this one. The accuracy here is 96%, right? And in this case, 96%, it's better than all those models. So when we have this, this one, it should be now logical because we have 4 models, and the accuracy of the ensemble, it's much better than each single one. But I don't know why this function calculate. Maybe there is a specific function for.
We actually get the same accuracy as the model 3 computing it by hand. So if we divide 14 by 143, we get this 9.7% misfit.
So this shape is not correct? This Y train, I mean this size? Because this is the size of my data, my test set, right? It's 14 divided by what? So print.
It's Y test, the shape of Y test, isn't it? For the
but Y train and Y test, it should be the same size, right? It's 426, right? $426, correct? So it's 14 divided by 426. How did you divide it?
But it looks like it's not the same size, because if we look at the confusion matrix, we never go up to.
Yes, yeah, this is correct. So why do we have this Y train?
Like Adrian said, I think it's about the Y test number. Or
sorry. It's not Y train. It's Y test, correct? Yeah, sorry. This one, it's Y test. I'm so sorry. Y test.
No problem.
Yes, this is correct. Y test. I wrote it Y train. But even if it's 134. This is correct. 19.20, correct? Which is the same here as this function. Now it's correct. Right?
Yes.
Yeah. I think we still have the same question, which is why is it exactly the same value?
Maybe it's by chance, right? It's just by chance. Maybe this model has been used for I don't know, because maybe it's by chance, because they are using, for example, 1, 2, and 3 for voting, and next time, I mean, for the first example, it was 1, 2, and 3. For the second, it was 1, 3, and 4. So by chance, we got numbers which is equal to L3, right?
I think so too.
Sorry. Then we were wondering why the accuracy of the final vote classifier is actually lower than some single ones. So it sort of means that it's not doing a good job, because
the ensemble for the hard voting or the soft voting?
For the hard voting, yeah, because we have like the first model has an accuracy that is higher than the final, than the combination of all of them.
Yeah, yes, this is. Yeah, but now we are not using a single model. We are using a combination of models, because all of them are voting. And when it's voting, so imagine that we are voting, are selecting the president, for example. Imagine that we are voting for Trump, selecting Trump. So votes of one who is working in MIT, it's the same as the vote of a person who is working in gas station, correct? So so both are equally, right? Do you know, in this voting, we might not select maybe the right person because of we are vote, but because if you are working in MIT and you didn't go for voting, so your vote will not be counted, right? And if you are working in MIT and there are 2 people working in a gas station and they selected Trump, imagine that we are a population of 3, and you are, I mean, we have all people voting, for example, and they have equal weight, for example. And the 2 people working in some place, they don't have knowledge, they don't have education, but they are more than the persons who have good educations. So they will just select what they want, because most votes will come from them, because it's a majority voting, right? So even if we have a model which has good accuracy, which is 93%, but because we are just to use, majority vote, for example, so it will be 1/3. I mean, this L1, his contribution to the final decision will be 1 divided by 4, right?
So perhaps model 1 and model 4 doesn't completely agree. They have a higher accuracy by themselves, but they don't predict the correct label at the same cases.
Yes, this is correct. Perhaps. Yeah, maybe. So in this case, we need to test it for model 1 and the model 2. We just need to calculate. I mean, we need to calculate this prediction one. For example, I can do it here. For example, is it okay to do it? Just to print those predictions, right? For model 1, I will just call it model 1, for example. Model 1. We can just test it, for example, to see, I mean, what is the situation. I will do it here. So we have model 2, model 3. I mean, we can see the difference. Is there any difference? Because we need to do it example by example. So this is 2, 3, 4. This is nice discussion, really, because, okay, why it's not? Can we compare? Or it will be difficult, right? No. So this is model 1. He selected the first one as 1. Model 2 selected it as 0. Model 3 selected it as 0. Model 4 selected it as 1. Right? Okay. Maybe I can. We can make model 1 minus model 2. Is it okay? Model 4, for example. If we need to predict, I mean, we need to see if they are fully agreed. Yes, yeah, you are right. This is model. I mean, I just subtract the model 1 from model 4. So there are some cases. There are four cases where they don't agree with each other. Do you see? So in fact, the model 1 and the model 4, they have the same accuracy, but there are 4 cases where they don't have the same opinion. Right? No, it's a 5. In fact, it's 5.
So another question could be, was it intentional that you chose 4 models in the ensemble? It's not an odd number like you.
No, it should be odd number. I guess it should be odd number.
Maybe then it's also not that easy to get this problem with hard voting getting a lower accuracy.
Yes, because I don't know if we have a case, for example, where 2 vote for one and 2 vote for another one, which one will be selected? Maybe it will select one by random, right? Correct?
Yes.
So in fact, we need to disable one of those learners. For example, it could be, for example, maybe perceptron, for example. But if I will make those changes, so I can just remove this. No, we can just keep it here because we don't have a problem here. We can go for that part here, and we can remove this. Can I remove it like this? Now we have 3 models, correct?
Yeah, I guess so.
Yeah, so we can just train test. Why we have this one? Because we need to remove one from here. Okay, so what will be the accuracy now? 92. Is it the same? Yeah, it's the same, right? 92. No, it's different, right?
Yes, it's higher now.
Yeah, it's higher than higher. It's 92%, right?
Higher than before, but still lower than model 1 and 4.
Yes, because model 1 and 4, they have different opinions. They are not selecting. I mean, they have the same accuracy, but in fact, they are not selecting the same. They don't have the same choices. Right?
Nice to see.
And in fact, when we removed also L2, because L2 has the lowest accuracy here, which is 85%, when we removed it, it enhances the results. Because maybe this one will make them confused, right? Or also he will be voting and his voting is not the correct decision, but even if it's not the correct decision, it will change. It will change the results and it will change it negatively because maybe he will put wrong vote, right? So he might wrongly, say that this one should be A, but it should be B. But because he voted with another one, maybe both of them will contribute to a decision which is not the right decision, but it will be counted and the total accuracy will be less.
But so if we get an accuracy at the end that is lower than one single model, in that case, the first or the fourth one, why don't we
select
for one of those if the final combination of all of them is giving an accuracy that is lower, and then like longer computation time and higher complexity?
Yes, because we mentioned at the beginning is that we try to reduce bias, for example, right? Because maybe this model, which is 93%, it could be overfitted, for example. No, but it has good accuracy, right? It could be close to overfit, for example. So it will be sensitive for variations or variance. It will contribute to variance, right? So it's just a way to get a kind of trade-off between bias and variance. So maybe even if you will get less accuracy, but it will be more robust.
Okay.
Right?
Yep.
Yeah, because the idea here is to try to get more robust results. And if you will try to increase the community, maybe you will reach the right decision. Although some of us are very clever. I mean, it's like voting here. L1 is very smart and very clever, and the L4 is very clever. But when we increase the population, the decision will not be based on a single one of them. It will be based on the whole population, right? So maybe at the end, I mean, results will be less, but maybe the model capability to generalize it will be much better. Also, the accuracy will be a little bit less because we need, as you remember, we have this curve, error curve, which is in one side it will be underfitting, and the other side it will be overfitting. We'll try to reach this middle point. So maybe if we have these combinations, we will be able to reach this middle point better than using a single model. Because if we will use L1, maybe this L1 it will be too much to the left, so it will be very close to overfit. So it will be more sensitive. The model will be more sensitive to noise. In my data set, for example, it will be sensitive to those small changes. But when we have this kind of ensemble, we will try to drag the whole performance to the middle of the curve. So we have a kind of trade-off between bias and variance. Is it something, it could be a logical answer like this? Yes. Okay, so any other questions, please? So thanks for this nice discussion, because it helped us really to understand what is going on. So those discussions are very, very nice. So thank you very much. Any other questions? Okay, so in this case, we will just stop here for 10 minutes, or we can start at 11:30. Is that okay? Yes, any other questions? Maybe if someone has a question, please. Oh, maybe it's me who is raising hand. Okay, so we will start again at 11:30. Thank you.